Okay, sir. Welcome back to the third session of the day. Now we have with us Dr. Manisha Paul, ma'am. Ma'am has worked in educational team at Mathworks and is based out of Kolkata. She primarily interacts with the faculty, researcher, and students across different domains to accelerate the STEAM education in India. She received her BTech degree from West Bengal University of Technology and ME degree from Jadavpur University, both in electronics and communication engineering. Later, she pursued PhD in computer science from Indian Statistics Institute, Kolkata. She has contributed to machine learning in healthcare during her ME optimization during her PhD research. She was also engaged in energy management research for smart building during a brief stint in France. She has published extensively and on internationally reputed journals and conferences on biomedical engineering, computational intelligence, and image analysis. So I welcome you, ma'am.
Thank you, ma'am. Thank you, sir, for the warm welcome. Am I open to share my screen, please?
Yes, ma'am.
Thank you. Let me know if the screen is visible, the PowerPoint presentation.
Yes, ma'am. It is not visible.
Okay. Thank you. Along with me, I have one colleague of mine also in the session, Dr. Shavik Chatterjee. So we are working in the academic team or the education team of Mathworks, and we collaborate with students, faculty, and researchers across India to have Matlab and Simulink as a pedagogical tool incorporated in curriculum. So we are talking about computational tools in this session and how this could be incorporated in power system studies. So this is how we generally work with educationalists in academia. So the faculties or the industry share a course outline on the syllabus, and different examples are getting mapped from Mathworks in the course syllabus, and that is how the industry academia gap is being bridged. These collaborations along with different institutions is taking around 6 to 12 months in nature, and if any one of you is interested, we are free to interact with you on a one-on-one basis after this session. So for this particular session, we are going to look into different aspects. First is like, why is modeling or computational tools necessary in power system studies? Next, we are going to talk about renewable grid integration a little bit. Then load flow analysis, how computational tools can help in such load flow analysis. And then fault is a very necessary thing in power grid, in the networks. So along with fault type classification, fault location detection becomes also necessary. So once we have spoken about all of this, we are also going to share some resources on how to get acquainted with Matlab, Simulink, and this kind of platform. So let's get started with the context first. So grid modernization is a mega trend. What is included in grid modernization? It starts from renewable energy resources, right? So on one hand, we have different photovoltaic or solar farms, wind turbines, and this energy is variable in nature. So that means this generated energy needs to be stored somewhere. So energy storage components such as battery, that is gaining attention as well. So because of this uncertainty in different data, this data is being captured and analyzed and studied, investigated in different areas. So each day around terabytes of data is generated in this manner, and this data forms an essential part of data analysis. Along with that, to oversee all of this, to have the grid as a stable network, regulatory bodies come into picture to oversee the interaction of these different areas. Now, if I talk about technologies, what are the different components that go into smart grid? Smart grid, on one hand, we have power system studies and compliances with different regulatory norms. On the other side, we have grid analytics. For example, what is going to be the demand of tomorrow? What is going to be the energy forecasted? Also, there is the IoT and OT applications. So different measurement is increasing in nature. So different Internet of Things, different sensors are measuring uh, values from different areas of this grid, and not only different areas of the grid itself. There is another important aspect, that is the energy management systems. So be it in factory, buildings, house, so energy management system is also developing in nature. So we have these different aspects, and for today's talk, we are primarily going to focus on how computational tool can be utilized in power system studies and compliance. So let me first take you through an application where Transpower has utilized Matlab Simulink in New Zealand's national grid as a reserve management tool. If you focus on their challenge, what they want to do is, what if the generator fails? In that case, does the grid have enough energy reserve stored in the grid itself to meet the demand that is there? So that is what they want to analyze. In case a generator fails, is there sufficient reserve power? Using MATLAB, what they have achieved, they have rapidly implemented the model. The simulations were easily verified with real data, and the updates were made in-house. There is a link to the user story that I have provided here. In case you want to read in details what they have done, it is provided in this particular link. And at the end of the session, I'm going to share the slides with you so that you can look up in these different links that are provided in different slides. So why simulation and computational models at all? What do we have in today's world? Aside from simulation model, why do we need computational capabilities? So the measurements is rapidly increasing in the grid technology. It is rapidly developing. So in these days we have pressure measurement units, synchrophasors, different kinds of measurements, so that we can precisely find out what kind of analysis or what kind of dynamics behavior is going inside the system. So we have grid data on one hand, the measurement data on one hand, and the simulated model of the grid on the other hand, the Simulink model. What can I do with these two? I can fine tune this model so that the dynamic behavior that the model is currently not capturing, that could be captured. So that fine tuning, that optimization, so that the exact replica of the electrical grid could be there, is known as digital twin. But why do we need a digital twin? We can replay different historical data, and we can simulate thousands of scenarios. Why do we need to simulate thousands of scenarios? Because like I mentioned, there are various renewable energy resources that are hooked up into the grid. So that renewable energy would be a very variable kind of source. So that variations needs to be captured, and under those circumstances, does the digital twin or the electric grid work fine or not? That needs to be analyzed. But we are talking about the Transpower application on the New Zealand national grid. So based on the simulation, what they did is they analyzed that using data analytics, whether the reserve and the forecasted demand are met or not. In case they are met, they repeat this entire process again after some time. In case they are not met, they repeat, they modify the controllers to meet this demand, so that this digital model could be more fine-tuned, so that the resources, so that the different other distributed energy resources could be more managed properly. And then again, this is repeated after a certain interval. So if I look into modeling approaches, like Dr. Tushar was talking just before this session, there are various mathematics that go into the this kind of modeling so that the different replica could be created. So those are first principle modeling. So you have talked about simulation model. So there is Simulinking coming into picture. So what if we don't know the mathematics? So then physical modeling could also be helpful. So this Simscape kind of environment helps in physical modeling of the system. This Simulink and Simscape, they gradually build up towards what is known as a system level design. What we are talking about right now is power system. So we wanted to talk about something that is a system, a grid, a network as a whole. So different design optimization also comes into picture. Of course, there are data-driven modeling on the other end. So what do we do with the different data that is there? So Matlab is able to support this entire ecosystem, and that's where this is why Matlab is so popular in this kind of electrical measurement studies. So first example or first step is we started the smart grid from renewable energies. So this is the grid in picture. There are different wind turbines, there are different solar farms, there are different distributed energy resources that is hooked up to the grid and the grid itself. So what do we want to do? When we talk about grid integration, what kind of compliances does the different equipments needs to be supported? Before proceeding any further, just let me mention that if you have any questions at any point of time, please feel free to type those in the chat window. Shavik is there and he will help me in answering some of this question. He will provide necessary links and supporting resources so that you can look up more in different areas. So, like I was mentioning, what is this compliance that we are talking about? So we have different energy resources that is connected to a point of contact. We have a voltage measurement at the point of contact and the frequency measurement. The voltage, there is a drop in this voltage at a certain point and there is a fluctuation in the frequency at a certain point in time. So what does the compliance do? Can I put a threshold over here? What is going to happen if I put a threshold over here and if the voltage exceeds that threshold, I'm going to just open circuit resource. In that case, since we are measuring this at the point of contact, I don't know which one to open. So there is a cascading trip kind of a situation and all the models are going to be open circuited, all the generators. And then what is going to happen? This will lead to a state of complete blackout. In that case, what we are trying to do is by imposing these grid codes, we are entering or allowing different bounds to this voltage and frequency, and this allows a little bit of fluctuation around the voltage and frequency. In this case, it is not going to trip. So let me go to Matlab and see if this could be implemented or what are these different grid codes into picture. So I'm going to open Matlab. I have a grid code, different files coded over here. So I have a grid code definition file over here, and this grid code definition file essentially has different timestamps, different voltages, different frequencies. So it is for different grid codes into implementation in these days. So I'm going to open the common grid codes that is out there, load the grid code definition file. But before that, let me say what this environment is. So can you mention in the chat window if you are familiar with Matlab LiveScript? You can just enter yes or no if you are familiar with Matlab LiveScript. No? Okay. Okay. Thank you. So those who are not familiar with Matlab LiveScript, let me go and open this window at first. This is Matlab's home environment. That is what Matlab appears as when you first launch Matlab. On the left hand side, you have the current folder. you can have a workspace where whatever variable we create that gets that appears in the workspace. Whatever is stored in the current folder, those are
Actually,
currently
ma'am,
executable. Yes.
actually, your screen is not showing, ma'am. Actually, it is hanged.
Okay. Okay. Thank you. Thank you for mentioning that. Let me reshare. Yeah. Is
Yes,
it
ma'am.
visible? Thank
Now
you.
it is visible. Yes.
Thank you.
So,
So this is the Matlab window that comes up when we launch Matlab. On the left hand side we have the current folder. On the right hand side we have the workspace. The current folder, whatever file is there, when we execute that, those files will execute, and when we save values, that would get saved in the current folder. On the top we have the ribbon. Various shortcuts are present over here. This is the command window. Whatever we write here, for example, I can write a equals to 2, and that will appear as a variable in the command window, in the workspace. That will store as a variable in the workspace. So let me clear this and the command window. That either way is going to just make the command window and the workspace busy. So what I am going to do is go in under the home tab and create a live script under it. So what happens when I create a new live script? This is untitled.mlx. MLX stands for live script. And you see on the left hand side, it is numbered as 1. This line, whatever I write here, I wrote in the command window a equals to 2. I can execute this line. On the left hand side, you can see this hatched area just turned blue. If I click on this, this will execute and the output is shown on the right hand side. So I don't have to go back and forth to see what is the output. I can write the code here. I can also write text here. So I can provide different documentation. I can insert equations, hyperlinks, images into this section as well. There are various live controls or live tasks over here, and I can add a table of contents. So in the result, this will have code sections as well as text section. So the benefit is that I can then save this or export this as a PDF or Word document and submit this as a text file, as a assignment, as a project report. So the reporting becomes very easy. Now let me go ahead and execute this one at a time. Before moving on, this is the grid code definition. I have stored this for different time and frequency and voltages. I have stored the definitions in this particular file. Now I'm plotting this for IEEE 1547, which is the benchmark for distributed energy resource grid codes. This is for a traditional one, and ERCOT is for wind farms in Texas. So if I execute this two different codes by just clicking on the blue lines here and here, this will give me the graph here. And I can pop out this graph if I want and make it more interactive in nature. I can play around, I can zoom in, I can do different other activities by going into this plots. So I'm not going to explore this plot more, but I'm going to go back here and bring to your attention that these two have different x-axis. The elapsed time on the left hand side is in linear scale, and on the right hand side it is on semi-log scale. And we have the three grid codes plotted over here. What does this mean? The bounds are there so that the voltage can write through the requirements. There is a mandatory requirement and a frequency and a voltage requirement. These are the mandatory requirement. What does that mean? In IEEE 1547 in 2008, this got a revised version. So in this particular grid code, there is a may run through and may be run through. So what does that mean? So this has a plot like this. So there is a bound where if the voltage and the frequency fluctuates, it must write through. This is allowed. If it is in the white region, this must strip. So this is absolutely not allowed. But if it is in the blue region, this can go for a maybe write. So maybe write means it is optional. It can either trip or might not trip. So if we allow it to write through in the maybe region, what is going to be the different activities, what is going to be the different performance. We can measure the voltage, power and all of this in the maybe write through that is of interest. So what I'm going to next do is plot voltage versus frequency this time instead of voltage versus time and frequency versus time. And we have this different square like interface. So this is like a Venn diagram, right? I just plotted this. This is like a Venn diagram. This black square is the average region where different voltage frequency usually operates. This blue line is the write through line. Even if it exceeds, even if it stays in the blue region, it is allowed to write through. If it is going into this orange region, it is sometimes allowed to write through. So this is the maybe region. And then if it is going into the red region, it must trip, right? So these are the different grid codes, different interpretation of the grid codes. And if you noticed, you can use live script itself to do your presentation instead of using the slides. So now let me go and take a real example. I'm taking the historical events and various phasor measurement units. So there are 12 events inside it. And what does each of these events have? Each of this CSV file has. Let me double click and open one of this. So if you noticed in the previous plots, we had voltage and frequency essentially to represent the grid codes. So I don't need the reactive and the active power and the angle for this to be represented. And then I can import this data. How do I import this data? I can click on this right to import this data into the workspace. So it will import as a table and 3 columns, the time, voltage and frequency. Or for electric for this kind of electrical operations, when we are going on a system level design, we want to have this automated so that we can reproduce this for several other events. So what I'm going to do is click on the import function and generate a function out of it. If I click on generate function, it is again going to return me the same table. It is going to take the file name and the data lines which I want to import as input, and it is going to write this import file function for me. I did not write this line and it was auto-generated in front of your eyes just now. If you notice the time 15 July 1529. So it was auto-generated in front of your eyes. I did not write, but I have saved this file previously, so I'm not going to save this file again. So I'm not going to save this file again, and I'm going to open what is known as analysis of the PMU data. This is another live script. I see a question, what is meant by ride here? So ride means the device is not going to trip. Just like I mentioned in the slide, the device is not going to get disconnected when the voltage exceeds the threshold. So there is small fluctuation. Since I am putting the bounds, here it is detected not to go outside the bound, so it is not tripping. So that is what is meant by, otherwise it is going to trip. So trip or ride, that is the two cases. Now let me go back to Matlab again. I have opened this particular live script. As I mentioned, I have imported the data and generated the file previously. So I'm going to use that and return the time, voltage and frequency. I am using here IEEE 1547, but I can use any other kind of grid code also. Let me use the ERCOT grid code first. For the PMU events, there were 12 files. I just selected 4 of the events, 1, 4, 7 and 11. it is going to plot now how the system is behaving, and under different grid codes, is the system behavior acceptable or not? Is it compliant or not? So the frequency write through is compliant, but the voltage write through, if you notice here, it is exceeding, the yellow line is exceeding the bounds. The red line is also exceeding the bounds. There is a little bit of exceeding here also in the blue line. So now I want to analyze this computationally. I cannot manually observe this for all of them. So I'm going to write a event analysis for this and generate a table. So it says this has tripped, event 1 has tripped at 1.7 second, event 2 at 0.8, and event 3 at 4 second. Event 4 has not tripped at all. So event 4, which is the purple line, this has stayed in the bounds throughout. The yellow, red and blue lines has tripped. But if you notice the blue line in particular, let me open this separately and zoom in here. I'm going to zoom in this region. So if you have noticed, there is a trip over here itself. While we were looking at a different region, we were looking at this region. This has tripped over in this region itself, much long before that region. So when this exceeds the bound, it is going to trip, and that particular energy resource is going to be disconnected from the grid. Means we have to control the system to operate only in the right voltage. Yes, that is true. We have to control the system properly so that it is within this bounds, so that it can write through. So now I'm going to go over to IEEE 1547, and let's see. This is interesting because what happens when it goes in the maybe cycle? As we have observed, all the frequency write-throughs are compliant, but what happens in the maybe cycle for the IEEE? Here the yellow has gone in the maybe cycle, there a little part of blue has gone in the maybe cycle, this red line has gone even outside the maybe cycle, so this is going to trip. Yellow line has probably tripped over here. The blue line has not tripped at all, and the purple line has also not tripped at all. So if we look into this, this has not tripped. This has tripped in the mandatory, the must write through, but in the maybe write through, it has exceeded in the maybe write through, but it has stayed within the must write through. How do I know that? This purple line, if I open this purple line, again I am zooming a little bit here. So this region was the must write through, and this is the maybe write through. It has tripped. So far what I am doing is taking different events and checking whether they are compliant or not. How does this help in the grid itself? How am I going to incorporate this with the simulation models? So the next thing that I want to do is to model a wind farm, a wind system inside the Simulink itself. So let me take an example simulation. I have you ever noticed Simulink before? Anyone has used Simulink, or anyone is there who hasn't used Simulink before? Anyone who hasn't used Simulink? Okay, so I guess everyone has used Simulink before. So just for those who are not aware, this is the canvas. It's like a white screen. Here we don't write codes. It's just a drag and drop based environment. Where do we drag things from? This is the library browser, and in the library browser there are different components. Simulink, commonly used blocks. We bring things from scope and subsystems and different other sources we can bring. For example, we can bring out a sine wave from here, or a step function from here, and the things are like a display block to display numeric values, or like a scope block to have something like an oscilloscope to display the signals. Also, if I scroll down below, instead of doing this mathematical constructs, we have what is known as Simscape over here. What is Simscape? Simscape is used for physical modeling. So these are like physical components. For example, if I go into the Simscape foundation library, in the electrical elements, there is this diode, capacitor. These are not equations, right? These are physical components that we can connect and build system out of. And then I can see, for example, let me bring the resistance into this resistor into the picture, or this inductor into the picture, and see what it's going to do. I have just dragged this inductor into the canvas. If I double click on this inductor, I can click over here, and this would show me what is the underneath equation that it is encoding. If I don't want this particular equation to form an inductor, if I want some other relation to form an inductor, I can encode that here, and of course make a copy of it before making any changes, and change different parameters from here. But we are talking about a wind farm. I'm not going to use an inductor over here. From the Simulink library, I have already created what is known as a microgrid library. The essential elements for the microgrid, I have created that. Let me just have this separately. Sorry for making the screen. I'm just making the screen compact so that you can see all of this together. So I have created a microgrid library from before, and I'm just going to drag elements from here instead from the Simulink library browser. So I have variable loads, static loads, different common elements that we use, relay, transformer, all of this. And this, I want to use a solar array over here and a wind turbine over here. So I'm going to use a wind turbine over here and a solar array over here. So if you notice, there is a solar array that is in PQ model and a solar array that is in EMT model, electromagnetic things. So if I double click on this phasor that says power GUI phasor 60 Hertz, I can change whether this is to be operated in continuous or discrete or other modes. So the phasor mode is fine. So I'm going to now connect all of this. Yeah. So I connected the solar panel with the 3 phases. There is a irradiance profile, which is just like a step input that is provided to this particular solar array. And I'm going to connect the wind speed now to the wind turbine that is there, and connect the different ABC phases. A, B, and C phases. So now that I have connected this, I'm going to run this model and see what happens. I'm going to run this model and see the output, the voltage and the power output. Can anyone tell me why is there a fluctuation or change over here at 5 seconds? What does this 5-second change mean? How did it come into picture? So that is where we use computational tools. How does this came into picture? Due to static load? Any other guesses? No other guesses? Okay. So we have a solar panel over here or solar array over here. We have an irradiance profile that I said as a step input. The step time was 5 seconds. So at 5 seconds, this irradiance was provided to the solar array and then it got active. So I'm going to change this to 2 seconds and see if there is any change in the output. So if I change this to 2 seconds, you can see this to move over here. So I can figure out why this change is occurring by varying different parameters, and that should be a good way to analyze different models in practice. I used a step input for the solar array and a 15 meter per second constant block for the wind turbine. But 15 meter per second is supposed to change throughout the entire day, right? You can use a constant block as well. You can use a sinusoidal block as well. Just as a source of input, I have considered a step input. So in the instead of using a constant block, let me do what is known as a TMI data. So from the microgrid, I'm now going to drag this TMY3 data that I have already loaded this with. So this is from Dallas, Texas. I can change any other place where this data is supposed to be loaded from. And if I plot the meteorological data, the weather conditions, so let me see what this is going to give me. So you can see from here, there is global horizontal irradiance, diffuse horizontal irradiance, direct normal irradiance, temperature, as well as wind speed. So the irradiance as well as the wind speed is given by this TMY data, and I can, instead of doing that step input and the constant block, I can use this as the data right now and then conduct the experiment. But that is, again, I'm just simulating the wind system, wind turbine. I have now the renewable form. I have now the grid codes. Let's integrate these two in practice. So let me close all of this. I have too many windows open over here. So let me open right now the Pmu Replay. So you have seen the Pmu data that I had previously analyzed. Different events were there. So in this particular model, what I did was, I have the wind turbine, the different speeds are there. I chose only the event 4 from here, from the Pmu data. It is connected to a replay block, then a transformer, different loads are connected, and at the bottom, if you notice, uh, yeah, uh, I am just trying to decrease the window size. There are too many windows right now. Yeah, I hope it is visible right now. Yeah. So we have the wind turbine over here, and at the bottom, if you notice, there is this grid code check, that is IEEE 1547, and there is this another block, that is IEEE 1547 voltage versus frequency. So what is happening here? I am loading the grid code properties again over here, and the voltage versus frequency part. Remember the square one, the different squares, nominal, must, may, and the must trip conditions. So that we are all loading, and we are going to see now the behavior and how the operating point is moving for this particular wind turbine in practice. So I'm just going to replay this simulation. And you notice this particular operating point is now going to move, and it is moving, but it is not at any point of time leaving the orange bound, which means it is throughout there in the maybe cycle. Sometimes it has exceeded the must cycle, but it was throughout there in the maybe cycle. I can repeat this simulation again for you to observe this closely. Will go outside the blue box, but it won't go outside the orange box, right? So it will stay in the orange box throughout, which means that this particular wind turbine is compliant with the grid codes, with IEEE 1547 grid code. If I look into the voltage and the frequency check, you can also notice from here, let me increase the figure size. You can also visualize from here that the must condition has been exceeded, but it was throughout there in the may condition. Similarly, the frequency was throughout there in the must condition itself. It has not exceeded the must condition also. That is good, but what happens when this this occurs? So this was the output of the wind turbine in particular, the voltage and the generated power, the reactive power and the active power, and then we have the wind speed. Wind speed has been maintained at constant, and when this trip has occurred, when this various fluctuations has occurred, the reactive power has increased to boost the wind turbine so that the wind speed has remained constant. So the reactive power has been provided in excess to maintain the wind speed. This is fine, but this was only for one event. I want to simulate this for multiple events. What do I do next? So let me open up another particular example. If you notice carefully, this is exactly the same example as before. Let me increase this. Yeah, I hope it is visible now. So what all changes I have made here? First of all, this was only for event 4. Now I have included all the 4 events, that is 1, 4, 7 and 11 that we studied earlier. I have incorporated different wind speeds now. This is not fixed anymore. At the bottom side, this grid compliance area, I have incorporated this particular block so that I can test for both must and may conditions, and then I store the value, the reactive power, because that is what we observe to change. So I'm going to store this particular reactive power into the workspace and see its difference. How does this change in must and may condition, right? So different changes. How do I do all of this? There is event, there is wind speed, there is must or may trip, and then store this. Do I do this manually for each of them? That is not possible, right? That is where we write Matlab script so that this entire thing could be automated. So what I'm going to do is, yeah, first let me start the parallel pool first. I'm going to use a little bit of parallel processing over here so that you can see. So it is starting the parallel pool on my local machine. So I can click over here and see what all machine I can start the parallel pool on. I am starting this on Matlab local machine. So this is going to use the different cores that I have inside my laptop. So it is going to leverage that. For example, if I write just a for loop, instead of for loop, I'm going to write a par for loop. It means parallel for loop, and I'm going to execute that from 1 to 10. Just display the loop variable, and that's it. Just this loop. It executes not in sequence. So whichever core finishes this first, that output gets printed before. So that is the use of parallel pool. You can see it is all the cores are getting used up, but all the results are also coming. So that's why this is not in sequential order. So instead, if I write a for loop, this will be in sequential order. So whatever operation is inside this par for loop, this would operate in individually in different cores. So I'm going to use this to have this particular thing known as batch sim events. What I'm doing here, I'm first of all opening this particular model that I have. This model, I'm going to open that. Then load all the 4 events that we saw before. Import the data using the script file. There are 4 events, 1, 2, 3, and 4. There are 4 events. There are 2 trip conditions, must and may, and wind vector I am using for stages. So 5, 10, 15, and 20. These are the 4 wind speeds that I am using. So 5 meter per second, 10 meter per second, 15 and 20 meter per second. How many number of simulations do I need to do? This is 4 into 4 into 2. That is 32 simulations I need to do. So let me execute all of this one at a time. I'm going to execute this first and then go to this and then set up this for, I'm setting this up for my particular machine. You can set this up for batch processing, different clusters that you have, anything else that you have. This particular command, if I use sim, it is going to use only 1 core. I have 4 cores in my machine, so I'm going to use par sim so that all of this runs in parallel. And I'm going to diagnose whether for different kinds of events, different kinds of wind speed, does my wind farm operates properly inside the grid compliance. does it stay inside the grid compliance criteria that has been set out. So you can see the Simulink, starting the Simulink on the different parallel workers. This will start individually on each of the parallel workers. I have 4 cores, so there are 4 parallel workers. Then it is loading the model on each of them. And then we will see the simulation run on different areas, on different cores. So we will see there are 32 simulations that are going to run, and how much time does it take, we are going to check that out. So you can see this has started, 4 of them has started, 2% it has increased, it has started saving up all the, backing up all the unsaved models before starting, and it has executed right now. So BGL Impal is my machine. If this is just the name of my machine, we can see the progress through all the 32 condition that is happening here. Instead of this list view, I can also have a grid view to see all of this progressing through the different conditions, through the different simulations. You can use this to, let's say this has taken 25 seconds, whereas this all has taken 4-5 seconds. So why has this taken larger amount of time? What were the conditions in which this particular event has executed? In case one of these errors out, the code is not going to stop. You can view the diagnostics from here, but all of this is executing thankfully perfectly. It is not giving me any error, but in case if it gives an error, you can see the diagnostics from here, and rest of the cores are going to continue to work on all the other event conditions. So all of them has executed 32 conditions in a few seconds. If I were to manually execute this on each of the Simulink conditions, this was going to take me a lot of time, right? So that's the benefit of using Matlab as well as Simulink in conjunction, in integration with each other. So let me move on now to the slide presentation. What do we have so far? Let me recap quickly. We have gone through these slides before. So we have IEEE 1547, 28 in the revision, that is the must write through and the may write through, and there is a criteria where it must trip. This is the voltage and the frequency plots. Then we assessed the grid compliance with various PMU event data, phasor measurement unit, the data that was actually captured from the grid. Then we modeled a renewable energy simulation using Simscape electrical. We modeled this wind farm and this solar array, connected that to the grid itself. Then we saw the controls and the protection of Pmu Data Replay. We saw that the reactive power goes up when this fluctuates, so that this could boost the wind turbine, 9 megawatt wind turbine, and the wind speed could, and the output could remain constant. And then we saw the grid codes compliance to be tested in parallel. We use the parallel computing toolbox that is installed or that is shipped along with Matlab, so that this is executed. We did not talk about this graph in particular. So once all of this has executed, what I did in the live script was, after this parsim has completed, I extracted the result, that is the Q out, that is the reactive power for may and must, and I plotted them one on top of each other. So you can see from this particular graph, if we are allowing a conservative approach, that is we are tripping after the must condition, the power provided is quite less, whereas if we are tripping after the may condition, the power provided is much larger. And if your devices are uh, specified to work in these different conditions, that is going to work very fine and going to give you a good amount of results. while all of this has been said, we are still now in a totally computational environment. The controller development environment is this Matlab Simulink. This has been implemented, tested, verified. Then what is the next step? So all of this Simscape components, the Simscape models, if I click on one of the Simscape model, for example, let me click on this wind turbine. This was my particular component under steps. I'm going to right click and check. I can generate a C++ code from here. This is going to give me a C++ code, and then I can deploy that on a real-time automation controller. So I can deploy this on a control system or a different other controller, that is hardware integration is possible from the Simscape model itself in the hardware. And then this needs to be hooked up into a prototype of a very big grid or a subnetwork of this particular grid, and this prototype could be tested. But for testing this kind of systems, what we normally use is the speed goat compliant hardwares. So these hardwares are readily this can be readily used with whatever simulations you are doing in Matlab Simulink, and those code can be converted into for hardware in loop testing. So this comes into picture, the speed goat solution, and real-time controller could be designed. So I am not going to go into hardware in loop particularly. This is out of the scope of this particular talk. But if you want to view this workflow in more details, you can click on this link over here, and all the codes that we discussed and are provided in this link. These are all freely accessible. So if I click on this link, it's going to take me to a file exchange window. It's going to load a file exchange window. So this is mathworks.com's file exchange. This particular code is compiled by Jonathan, who is also a Mathworks staff, and these codes are all readily accessible by different users. But aside from Mathworks staff, because the staff level is there specifically only for Mathworks staff, for others also there are various file exchange codes that are shared by different authors who are Matlab users, not specifically Mathworks employees, Mathworks staff. So there is a community of resources in this file exchange. Around 40,000 files have been shared so far. So please feel free to explore this if you have. Power system is a very big area which you can understand from the FTP. There are 5 days, so many talks. So covering all of this in its entirety, it's not possible. So you can explore all of this so far. So before I move on to flow analysis, is there any particular question that we can address? Okay. Shavik, do you want to add anything more to this particular workflow?
No, I think it's good.
Thank you.
Yeah.
Okay. So can anyone tell me what is happening over here?
Hello.
Hello?
Ma'am, Anil Tegade sir. Hello.
Hello?
Anil Tegade sir, you want to ask any question?
Yeah, ma'am. Actually, very good afternoon to all, respected sir and ma'am. Actually, I had raised the question. Actually, I had done one simulation in 2015 version, and I just wanted to open that in 2010, but
Okay.
not able to open that. Multiple errors are there, ma'am. So will you please help me out?
Sure. That particular thing, for example, if I open Simulink, just give me a minute. Yeah. If I open Simulink, any model that is there, that could be saved into older versions. I can export this model into previous version. Have you tried this particular option? Then it might become compliant to older versions. I can select which release I want to select this model particularly for.
Yeah, ma'am. Actually, I tried with the help of that whatever the mathworks.com. I got the information about the same. I tried it also, but
Sure.
the version that 2010 R 2010 I hadn't got in that. Whenever I gone to the save as type, I went through that thing,
Sure.
but I haven't found that thing, ma'am.
Okay, we can look particularly if you want to catch up after this session, we can particularly look into your code by screen sharing and then try to debug this.
Sure,
Or you
ma'am.
can
Sure,
write to us and we will be able to support you more.
sure, ma'am. Thank you, ma'am. I'll
Thank you.
take your
Just
mail
a
ID
follow-up
from
question.
organizer, ma'am.
Yeah. We will definitely share our email IDs at the end of the session. Don't worry.
Sure, thank you, ma'am.
Thank you.
Just curious, sir, why do you want to open in 2010? Is there any particular reason you are looking for?
Anil sir, what Shavik is asking, why do you want to open the models in 2010?
Yeah, actually, sir, one of my friend, he is stuck in his MTech project, and he actually other version is not able to install in his system, sir. So he is only
Oh,
having
okay, okay,
2010 system, so that is the reason, sir.
okay,
Sure.
Yeah,
okay. Because yeah, I mean, one of the challenges is some point if if there are like drastically things have changed, then something in the model cannot be gone to a previous version as well. If that
yeah,
toolbox
right.
even does not exist, then that is not
Yeah,
possible.
right, sir. I got you, sir. But actually, the main reason is something different, sir.
Okay, okay, got it.
Yeah, thank you, sir.
So just like I asked, what is the difference between the two things that is happening over here in the screen? If I can execute this once more, yeah. So any guesses? What is the difference between these two? Shavik, do you want to guess?
Uh,
So what is happening over here is on the top model, on the first model, uh, we are manually placing the different blocks and connecting. And on the bottom model, a code is being used to build this automatically. So the build time is much faster. Why do I need this? This is just a simple model and it could be easily built by click and drag. But if I don't write a code for automatically building this model, it is how do I build a model for scaled up system? What do I mean by scaled up system? So how do I build a network? A network, we fetch the data from different specification. This could be in different data sheets, spreadsheets, that is stored in that is imported into Matlab data structure. Then different scripts are created to create the Simulink model, and this Simulink model and the speed growth ready solutions are then available to the users. So this is the general workflow for large scale electrical models. So this is an example. This is IEEE 123 node test feeder, and imagine the amount of click and drag that you have to do and you can mix up in the system. So this file is also available in file exchange, and it is just a simulation of how this network is appearing when the automated build code is written and executed. So while we are discussing this, let me open a small scale version of this and understand how do we analyze the different load flow through this particular circuit. So there are different inbuilt exercises that inbuilt examples that could be executed. Let me close the other files. I don't like too many files open at a time. So I'm going to clear the workspace. Yeah. So I have a inbuilt shipped with MATLAB file. Whatever comes with power that are power system examples. So you can see there are various power system examples in there. So what I want to do is a load flow network analysis. So I'm going to type load flow network, and I want to do it for a very small network. Only 5 buses are there. So let me type that and click enter. This is going to open the shipping example. Shipping example means this is already shipped with Matlab. Whenever you install Matlab, you can open this up by typing in that command. There are different load flow bus blocks. There are different load flow blocks. Different generators are there. Different P-type, PQ-type, Z-type, different loads are there, dynamic loads are there, asynchronous machines, synchronous machines are there, and it is connected through a 25 kilometer, 25 kV feeder, right? So this is again in phasor, and if I run this code, it is going to execute, and at best I can view in this scope the synchronous machine, asynchronous machine, and the dynamic loads that are out there. But we want to do a load flow analysis. What should be the initial parameters that could these different loads could initialize with? So what I'm going to do is double click on this phasor GUI. In the block parameters, there is this solver that is phasor that we looked into. We can change this into different other type of solvers. So I'm choosing the phasor solver for this particular application. Under tools, there are various other kind of tools with the impedance measurement. If I want to do a Fourier analysis, I can do that as well. I can do different power line parameters, change them. So what I want to do is load flow analysis. I will click on this load flow analyzer app for this particular network, and this is going to give me a table. What does this table have? Different block names, block types. As I mentioned, there are PQ-RLC loads, there are dynamic loads, there is Z-RLC load, Z type. So shunt parameters, and also you notice there is one particular line that has 0 reactive and active power. What does this load flow bus 3 line mean, and why is in there a load attached to this particular line? So you notice over here there are different load flow bus blocks. This particular block does not have any load particularly attached to this line, and since this does not have any reactive or active power, that's why this is 0 in load flow. But why is this there in the table? So that all of the buses could be visualized at a time. If I look towards the right hand side, there is this load flow voltage, angle, reactive and active power, but all are 0. So for this particular network, I can calculate this by clicking on the compute button and check whether this meets the system specification. If this meets, this load flow has converged, I can click on apply to apply this solution to the model. I have already this as applied because I did not change anything in the model. But if you want to change the parameters, in case this has not converged, you can double click on this and change various parameters over here. Rerun this again, update this model with the change parameters, compute again, and then click on apply. Fair enough. This is the load flow analysis analyzer app. But what Matlab helps you to do is to get this reporting out of it. I can choose a report format, get this in Excel. Let's save this somewhere here. What does this Excel look like? Let me open this Excel file. Let me open this in Excel itself. If I open this in Excel, what do I have here? The total generation, total PQ load, Z shunt, asynchronous machine. First line is how much power is generated in this particular bus. How much power, reactive and active power, is generated. PQ load and Z shunt load are how much power is absorbed in this particular line? And what are these two? Any guesses? This is how much is generated, this is how much is absorbed. What is this two? These two are how much power is transmitted to the neighboring lines, because B120 is connected to B13.8 and 25_1. Let's check. B120 is connected to B13.8 from this particular branch and B25_1. So these two are the neighboring branches. So last two lines are how much power is transmitted to the neighboring buses. So that is the load flow analyzer report. We can have all of this separately if you want, but this is the summarized report that is out there. That is automatically generated from the load flow analyzer app. So next thing that we are going to talk about is grid fault location detection. We can do a fault type detection also, but I'm going to do a grid fault location detection. Before that, this particular study was done by Hydro-Quebec IREC Research Institute, and Hydro-Quebec is a collaborator with whom Mathworks has designed this particular library of Simscape Electrical. So what grid fault location detection will do? So there was this MILES project from this particular research institute. What does MILES project mean? It means maintenance and investigation of lines. There are different fault location. This was the real fault location and the fault location detected by MILES project. You can see these are very close enough. The data, the location could be triangulated, but how? How do I get this data and triangulate this location? So this is the system, this is the network they had replicated for the grid. This is the digital twin of the grid. There are voltage measurements in these green blocks, and they have introduced faults in these red regions. There are 38 red regions, and they have introduced various kinds of faults in these regions. And then they are going to save this particular simulation. They are going to execute this simulation, save this simulation data, and do a classification learner app or classification method, data analytics on this. How is that done? For each line, if you notice, there were 1, 2, and 3 lines over here. Each of this is 5 kilometers, so the total length of the line is 15 kilometers. So each of the 1 kilometer lines, each of the 5 kilometer lines is again split into small 5 kilometers parts. So fault is introduced in this different ABC. This could be a 3-phase fault or a 2-phase fault, single phase fault, and it could be introduced in this 1, 2, 3, and 4 locations, and we can study the behavior. Let me show you how this fault is introduced or injected into the grid network and how this data is captured. Like I mentioned, I'm going to use a script for that. So I'm going to use a grid fault location. Instead of using a direct MFile or MLX file, what I am using here is .prj file. What does prj file means? It means a project file, and whatever folders, files are there that are together compiled and stored in this project file. The benefit is that it always analyzes the dependencies on each other and starts up with something, it adds various functions, and I can get the functions that I am supposed to load from here. So this is a very user-friendly repository or user-friendly approach of storing Matlab files when the project grows in size. So you will have different Matlab files, as you have seen Matlab and Simulink integration with each other. There are various Matlab files, and they combine with each other very nicely to give you very beautiful network analysis, load flow analysis. So multiple files, how they that could be handled is using this kind of a project. So I'm talking about generating synthetic data. So I'm going to click on this particular, and there is a Simulink file for that, the 125 kilometer line and 25 kV network that is out there. So I'm just going to open this file. This is a bit longer file, so it will take a while to load. Just bear with me for a few seconds. Yeah, it is going to take a while to load. So yeah, it has opened up. As you can see, it's the replica of what was there in the slide itself. So there are different voltage measurement places where the voltages are measured, the voltage sag measurements. Each of these lines are 5-kilometer lines, so fault could be introduced in these regions. So there are other kind of lines also, the two-phase lines over here, single-phase lines over here. So all of this is there. There are different load flow buses to measure the load flows over here. What I am going to do is use this fault block. What is this fault block? It has phase resistance and neutral resistance. I can introduce different combinations of phase resistance and neutral resistance in different phases and drag this fault block over this particular line or this particular line or this particular line. So I'm just going to drag this, not manually using a program. So I'm going to connect this in different places. So how am I going to do that? How am I going to synthesize that data? I have the script written from before. So generate fault data. For that, I have ABG fault. What is ABG? AB to ground fault. I can have any other 3 phases fault if necessary. There were 10 lines. I have labeled each of these lines, and I can select the lines through which this fault is supposed to run. For the generating this synthetic data, 38 fault location, there are 288 combinations of those resistances that has been simulated. So 38 into 288, that is something above 10,000, and it is going to take me 24 hours to synthesize that data. That is not possible right now. So I'm just going to reduce these numbers to show you how this looks like. So I'm just going to do this for 2 lines for now. This line could be faulted, and I can add that fault block. You can see the fault block is there. I can add this in different places. Then I can set different parameters over here. For 3-phase fault, for 2-phase fault, I will have different parameters over here. Set those parameters. Then for each section, I'm going to add a line, right? Line fault. So now we will have those phase resistance and neutral resistance, different values are there. This could range in this order, and hence 288 faults could come up. But for now, I'm just going to use only one resistance value for R phase and only one resistance value for R neutral, and I'm going to run this code. So you can see this Simulink block automatically popped up. I did not click on anything. It is compiling. It is using ODE3 solver for solving the different differential equation that Dr. Toshar was also talking about. And you can see this block is getting connected to different locations in the grid itself. So I'm just I have just selected 1 and 5. So it is right now moving through line 1, and it is getting connected to different locations of the line and injecting the fault resistance in different places. So this fault is getting injected in line 1, and then it will get injected in the single phase line, that is which we selected as the 5th line, 5th bus. And after this, the fault type, this block ABC 3-phase and neutral, this is again going to change to A and N. This is the 5th block, which is the single phase block. So just let it load and compile the first iteration and you will be able to view it. So yeah, the fault block is now getting connected to A and in. So this is like the single phase line. This will again simulate for each of this location. Yeah, just give it some time, and then what is going to happen is we are going to extract the result from here and store it into a table variable. So you have seen how do we extract the Simulink result to workspace. We are going to do that and store that Simulink result into a table variable. Then we are using that table variable for fault location detection. So we have done the for loop so far. We have different values in different variables, and this is stored in this t variable. Now, how does this t variable look like? If I open this particular positive, negative, zero sequences from voltage measurement, if I extract this, it will give me something of this sort, this table. This is particularly for bus 1, magnitude, angle, and the label of fault, where the fault has located. 38 fault location, 288 fault. So that is 10,000 simulations. And if I look into the command window, it is going to give me a similar kind of table. So this was the table that has generated for voltage, angle measurement, magnitude and angle measurement for P and Z sequences. And at the end, there are the type of fault where the fault was injected. So since we have only done for line 1 and line 5, those are the fault location it is currently showing. But in actual synthetic data for all resistance values and for various other lines, it is going to give me a large volume of data set. So next thing that I'm going to do is get training data. Click on this particular file. What this is going to do, I have already generated the synthetic data, stored it, all the 10,000 rows. So I can just load this particular variable from the workspace. This is what is known as classification learner. Before I do that, if you want to load the classification learner, you can also go under apps tab, and there are numerous apps over here that users could use and simplify their workflow. Somebody was asking in the previous session if we want to use DSP for controller design. So there are numerous signal processing apps also. For the machine learning and deep learning part, this is the shelf of apps that are there. So we have deep network designer for deep learning, classification learner for classification, which is a supervised learning, and also we have regression learner, which is another kind of supervised learning. So this is the bunch of apps that we can use. We can also type it out over here, classification learner, and this will come up. Once this comes up, it will pop out a similar screen like this. What do I have in the workspace right now? I have this t variable. Why is this t variable here? It is from the synthetic data that has been generated, and you can see here there are around 10,000 rows here and 19 columns. Why 19 columns? Here for the small simulation we saw there were 19 features, so there are 19 columns, right? So what we are going to do here is we are going to load that particular variable t from the workspace, and it has automatically chosen from the response of that particular data set as fault. So you can see there are various columns in this particular t variable. 19 columns are there, and at the last there was this fault column. This has been chosen as the response variable. Why are there 39 particular types of fault? We talked about 38 faults, right? Why are there 39 types of fault? Because the other case is of normal. So there is 38 plus 1, 39 faults, and I'm going to use a cross validation of 5-fold and start the session. Let's see what happens. It is going to load the data into this particular space and give me a scatter plot. It is going to label, yeah.
Ma'am, class label is mentioned or not in the data? Is it
Class,
supervised?
yeah, it's supervised. The class
No.
level is the different types, different location where the fault was introduced.
Okay, so it is the last entry in a
Yeah.
particular column.
Yeah, so in this particular table, it was the 19th column, the fault.
Okay, okay, ma'am. Thank you.
Thank you. So this is the scatter plot. What does this particular scatter plot of the 1000 observations tell us? If you notice in particular, if I hover over here, it tells me these are the group of points which corresponds to the class normal. The normal is red in color. There are other group of points which are nearly red in color. These are not normal class. You can see L1 section 1. You can see this is L1 section 1. You can see here also it's L1 section 1. It's L1 section 1. But this particular red color, it's normal. So all the normal simulations are kind of easily segregable. This could be classified very easily, but all the other faults, they overlap in nature. Now what do? I can use the parallel pool that is there and use this particular option of all quick to train. But if you look into this particular scroll down menu, there is decision tree, discriminant analysis, logistic regression, naive Bayesian, support vector machine, k nearest neighbors, ensemble classifier, and neural network. So various kind of classifiers could be trained. I'm just going to do all quick to train. So it is going to train on all the easily trainable classifier which are quickly trainable and give me the various values. So note that it is training on 10,000 data, so it is going to take a while to train. But since I clicked on use parallel, it is going to train multiple classifiers in parallel. So once these are trained, yeah, this is 14% accuracy, not a very good accuracy. Let's see what the others said. This is 40, this is 75. You can see the accuracy is going up. So it depends on the application, what kind of classifier you are choosing, which is the good kind of classifier. So the other classifiers are still running. Yes, sir, you have a doubt?
Ma'am, just a small doubt. Let's say classifier performance are very much critical to the parameter selected for a particular
Absolutely.
classifier.
Yes.
So what is the process in this case if I want to find the optimal parameters for any classifier? Let's say for SVM it is C and gamma, or maybe for the random forest it may be the number of trees it generates. Is there any provision for selection of the parameters here?
Yes, thank you for that question. So I'm just coming to that question. Just give me a minute. Yeah.
Okay, ma'am. Thank you.
Thank you. So this is still executing in different trainings are still executing. I'm just going to stop the cubic because I know it is going to take a while to train the cubic one. You can see so far I have got a good accuracy of 92.9%. What are the parameters used in this particular KNN block? Here there are number of neighbors, 10. The distance metric is selected as Euclidean. So just like Sir was pointing out for SVM, there for KNN, these were the default parameters that it has trained with. How do I choose the optimal parameters for KNN? So I can go under this particular menu. Under KNN, there is something known as optimizable KNN. I can click on that. So this is the optimizable KNN. I can choose a solver for this optimization problem. Let's say Bayesian optimization. I'm going to execute for 5 iterations just for the sake of demo, but this should run for quite a few large number of iterations. The default was 30 as you had seen. So I'm going to use for 5 iterations, and in the advanced settings, I can choose which all are the parameters that I want to train on. So for SVM, like sir was saying, it would be the cost or the kernel parameters. So for KNN, it would be number of neighbors, the distance metric, the distance weight, and whether to standardize the data or not. If I don't want to choose one particular parameter, let's say I want to fix it to only one nearest neighbor, I can turn this off and select that particular value as constant. But for the sake of this example, let's train this on all the parameters, and then I can click on train. So this is the step of hyperparameter optimization and the minimum classification error that is going to happen. This curve is going to show up in just a minute, and as you can see from here, it is going to vary the number of neighbors in a large range. The distance metric could also be varied. The distance weight is varied in different formats, different formulas, and whether to standardize the data or not. So the minimum classification error curve will go down for estimated and observed, but it is going to take a while because this is a very large data set, right? While this is happening, let me go back and select this particular one. Okay, I cannot do that because it is executing still. So let me give it some time to optimize. I have selected 5 iterations, so if one iteration is taking so much time, you can imagine how much time it will be taking for 30 iterations. It's just because the data size is very large, but otherwise it's quite fast in nature because the other optimizers the other classifiers got trained in a very few seconds, right? So this took around 1 second, this 1.5 model. So model number 1.5 took just 68 seconds to train on such a large data set. So I'm going to cancel this for the time being because it is taking a lot of time, but this is how you can vary the
Okay, ma'am.
optimizer parameter.
Got it, ma'am. Thank you.
Thank you. Yeah. So you can see the cancelling is also taking some time. So it says here cancel training. This might take some time. So for this particular observation, I have the observation saved. So while it is getting cancelled, let me go back to the presentation and mention about that. So this was the model. We have different measurement places. We have introduced faults in 38 locations, done 288 simulations for each fault location, measured the table PNG sequences for different bus magnitude and angle. So we got the different fault locations. The code was something like this. So because we wanted to automate this process, we did a couple of simulations over here. This is just a snapshot of the voltage sequence data for different positive, negative, and zero sequences. But this is the output that I wanted to focus on. So this output was taken by using the classification learner app. This is the confusion matrix. I'm going to zoom in just in a second. This is using the quadratic support vector machine, and it gives surprisingly 89% accuracy. But if you notice carefully, if I zoom in, if you notice carefully, there is some overlap or misclassification in the let's say phase 2 L1PH2 and L1PH3. Similarly, there is some overlap in L1PH4 and L1PH5. Others are quite nicely in the diagonal areas. Also, this has the normal values have quite nicely classified. Okay, this is not showing the normal values. So in the simulation that we were doing, it will show the normal value. But the others are on the diagonal lines, and L1PH2 and L1PH3 are overlapping. L1PH4 and L1PH5 is overlapping. Why is that? And how can we improve that? So This is just taking one measurement, one bus voltage instead of taking all the bus voltage, if that improves the accuracy or not. This in fact deteriorates the accuracy. So if we take measurement in multiple places, that is good for the data set itself. So what has happened is L1, PH2 and PH3 were overlapping, which means that the line where the fault was detected was correctly classified. But since there were forks in the lines, where the forked error has occurred or where the fault has occurred in the forked regions, that was not very much evident from that. So let me see if the classifier runner has completed. Yeah, so I can go back here. Okay, no, it has still preparing to stop. It has not yet cancelled. So I can view the class, the model itself. Yeah, it's taking a while to load. Just give it a few seconds to load. So if I, yeah, I have the screenshot of the model, right? Yeah. So if I have the model here, if I look particularly here in this L1 PH2 and L1 PH3 regions, the branching from L2 line, after that there is a fork from 1 and in from L1 PH2 to L1 PH3. So when this kind of forks occur, this kind of forks is not there in this particular line, not there in this particular line, but again there in L1, PH4 and PH5, this kind of a fork. And when this kind of forks occur, it becomes difficult to specify where exactly the fault has occurred. So that was the underlying message from this particular experiment. Although the data has been synthesized and the classification learner has been trained, this becomes overlapping in nature. And how to detect that? When forks has occurred, this particular overlap has been prominent. So fault has been detected, but location could be either fork 1 or fork 2. It's difficult to say which one it is. So what additionally it was done at the end of each of the forks, so they have taken additional measurement. So if there are n forks in the line, you will need n-1 measurements. So because there was 2 forks, we will need only one measurement, one additional voltage measurement to measure the voltage difference between any one of the forks. That could be additionally supplied as a feature, and that will improve the output. I am not going to delve deeper into this particular classification problem, but if you want to know more about this workflow, you can just click on this link and view the results. So what were the key takeaways for this particular, these different workflows that we had shared? We had done thousands of simulation. The 10,000 simulation took 24 hours of time. The 32 simulation took a few seconds in front of your eyes, right? So simulation of data is very much necessary. Why? Because the renewable energy resources were variable in nature. So reduce your efforts on simulation models with computational capabilities. What was the title of this talk? Why we wanted introduction to computational tools for power system analysis. Matlab enables domain experts to do data science. In case you are not familiar with data science workflows, in case you are not familiar with machine learning workflows, you are just familiar with, let's say, power systems, electronics workflow, you did not know much about how to implement classifiers, what all parameters does each of the different classifiers need. You can just use the classification learner app and apply advanced analytics techniques. Similarly, there was a deep learning app also if you want to go much more deeper into data science workflows. There are Matlab Simulink methods to automate reports. For example, you have seen the live script, which could be converted into a PDF report. Similarly, you have seen the live load flow analyzer app, from where you can extract the Excel file, which gives you the report of amount of power generated, amount of power absorbed, and amount of power transferred to the next neighboring bus. So this saves time and kind of gives you a comprehensive report. Now, initially we looked into this particular picture and we mentioned there were three things: power system studies and compliance, grid analytics, and IoT OT applications. These two we did not talk about in much details, but if I go into this particular link, it has opened up the link in here. It talks about AI and IoT for grid analytics. Develop the grid of the future using AI and digital twins. So how does the AI and digital twins work together in hand? That could be understood from here, using smart utility infrastructure or various other examples, energy and price forecasting. There are different videos to learn from. There are different toolboxes. The documentation page is very nice. There are, just like we noticed about Hydro-Quebec and Transpower in New Zealand and Hydro-Quebec in Canada, there are various other organizations that are using Matlab products for this particular domain of power systems and utilities and energy. So you can read about all of this from this particular page, right? So all of this goes very nicely. Aside from that, let me open another page. This is Matlab videos and webinars. If, like I was talking about the energy forecasting, which is a part of the grid analytics workflow. Yeah. So there are various recorded webinars. This is long-term energy forecasting. This is for econometrics. This is for energy forecasting using machine learning and deep learning. So you can similarly search over here, going into Matlab webinars and videos. Someone has a request of please share link of this Matlab based apps. Sure. The apps, there are numerous apps for the classification learner. Let me see if there is a video for it and I can share that. Let me check the classification learner app. The first one is only the classification learner, and I can share this particular link with you so that you can read about this in more detail. So similarly, there are various other apps. Let me know which one you are interested in particular. I can share that with you. Like I mentioned, I have specified various links in different places. I will share the slide deck with you, so you can just explore that with to get more details about this particular workflows. So in Matlab, there is Simscape Electrical. That is a particular library we have seen in Simulink. This was developed in collaboration with Hydro-Quebec. There is a specialized power system underneath Simscape Electrical. As you notice, Simscape Electrical is a combination of Sim power system and Sim electronics. So there are various specialized power system block sets. The seminar before this was on facts. So StatCom, UPSC, all of these are inbuilt components in facts. There are renewable energy like wind turbine models that we have seen. There is also another page specifically on Simscape Electrical. How do you go to this page? Just click on this links source that are there in the slide deck. So how do you go to Simscape Electrical? You can just click on this source page and it will open the Simscape Electrical documentation, or what we say as the product page. So this is going to talk about how do you model, simulate electronic and mechatronic and electrical power systems. So getting started with different kind of options, fault tolerance, model deployment, Simscape platforms, all of these are there with different examples are there, different other Simscape designs. For example, we are talking about electrical. So what if you want to do something related to heat transfer? When you are talking about power electronics model, so heat transform, thermal effects of this forms a very integrated part of this. So combining this together is essential as well. So all of this goes very nicely, fits in very nicely with each other. So aside from that, there are various training on MATLAB courses that you can take. Even if you don't have MATLAB, you can use various training. You can access various trainings. You can see all of these are free trainings. This is available in Matlab Academy courses. These are all self-paced, means you don't have to sit through the entire course at a stretch. All of this will nearly take you 2 hours to complete. It did not require you a MATLAB installation. Many of these are browser-based. If you are interested in data analytics, machine learning on-ramp could be recommended. And at the end of this, it will provide you a certificate. Let me show you this quickly. If I go to matlabacademy.mathworks.com, this will open. Because I'm signed into this is going to open my page. So the first step is to create your account. The account creation is free. Then it will come through these various courses that are there. Yes, I'm going to share this link, matlabacademy.mathworks.com. If I open this in before signing in, before logging into my own account, this is going to open a page like this, Learn MATLAB for free. There are various on-ramp courses. These are free. If I go into this page, after logging into this account, you can also generate your own certificate. For example, I'm generating this certificate for image processing on-ramp course completion certificate. I have completed 100% of this course. If you want to give this out as assignments, we know many faculties are doing so. So please feel free to do that. This is often given out as assignment. I believe in electrical EEE courses, control design, signal processing, even Matlab, Simulink, Simscape. This forms very essential part. In case of battery modeling, also state flow analysis is a very essential part. Similarly, if you have access to, there are various other courses. If you have access to the campus-wide access suite, so you will have access to all of these courses. There are around 20 courses if your institution has access to MATLAB campus-wide suite. In case you don't have access to Matlab campus-wide suite, Matlab does give out trainings which are instructor-led. These are, of course, paid in nature, aside from the on-ramp courses which are free. These are free, as it is mentioned over here, but the longer ones, more than which span over entire day, those are paid in nature. Aside from that, our partnership, the academic team, it is not paid. It is available to all the academicians across India. So you have MATLAB platform, you have your expertise, your workforce, and you want to build them. You want to make the courses more engaging. You want to make your students more industry ready for tomorrow. We have our expertise that we can combine with your knowledge, your syllabus, your institute's mission and vision and core values, so that best of both worlds could be accessed. And many institutes are collaborating with us. Like I have mentioned, the collaboration takes around 6 to 12 months. These are our email ID. Shavik, I think he has another meeting, so he has left. But these are our email IDs, and if you want to join at LinkedIn, that is also fine too. I'm going to share this link in the chat window. This is the feedback link for Mathworks. At the end of the feedback link, when you submit the feedback link, you will have my email ID, the courses, link to the courses, and the link to the slides. So if you want to submit a feedback to this particular session, please feel free to do so, and you will have access to the slides. So what does this feedback link has? Let me show you that quickly. If I open this particular feedback link, this is going to ask you to recommend Mathworks support to a friend or colleague, your full name, uh, your email ID, department, so that if you have any doubt, you can just mention that as to us, and we can reach out to you if you are interested in anything similar, any institute, university, organization, which of the particular workflows was relevant for your particular research or your particular subjects, courses that you are offering, which of the topics studied or topics of power system studies are you teaching in this upcoming semester, or any other research projects that you are working on. If you mention any details over here, we can reach out to you. If you would like to have conversation with educational technical experts like us, or sales member to have a trial, or training consultants to upskill your team, so you can mention that, and phone number or any other feedback which you want to specify, any challenges that you are facing. So once you fill out this form and click on submit, you can have the slides downloaded from the thank you acknowledgement page. So let me check the Mathworks again, if the uh, simulation has ended, that particular. Yeah, so that has ended, so I have cancelled that, and I can click on this and generate the confusion matrix from here. I'm just going back into this workflow just to mention two more things. One is that I can export, plot, or I can save this as a JPEG file to paste in the papers. I can generate a function out of it, just like I have seen for importing files. And also I can export this model or generate a code out of it. So if I export this model into the workspace, let's say I am mentioning this as the trained model. In the workspace, it is going to specify in the workspace how to make predictions on this stability. I am going to use this particular function to make predictions. So all of this is automatically given as instructions, as guidance to you. And if you want to know in more details, there are links in various places. You just have to click on these links. There is what is confusion matrix. If I plot a ROC curve, that will show up what is ROC curve. Let me show that. Yeah, what is ROC curve, or just like you have clicked on prediction, so how to predict using an exported model. So all of this are there. You just have to know the right link to search for. So I will end the seminar here, and if you have any questions, please feel free to ask that.
Hello.
Hello.
Yeah, good afternoon, ma'am.
Good afternoon.
This is Satvi Singh from Bajaj Institute of Technology, Varda.
Hmm?
Ma'am, how can I extract? Suppose I have IEEE standard model benchmark example, and I have done some load flow study, and I want to extract the dynamics of that model. Okay, suppose there are 10 generators, and I want to extract in terms of in the form of state space. So
State
can I
space.
do that or not?
State space.
Yes.
Okay. Yeah. At the background of the load flow analyzer app, it is solving a Newton-Raphson method. So it is solving a state space model. But how do you extract that particular state space equation? There is a state flow functionality also in Simscape, in Simulink, that you can do various kind of workflows there. But for that, particularly from load flow analyzer app, I am not sure how do you extract that, but I can, if you specify this in the feedback form, I can definitely look this up and get in touch with you.
Sure, ma'am. Sure, ma'am.
Thank you.
Thank you, ma'am. Thank you a lot.
Ma'am, actually, I'm having one query. Ma'am, actually, you have mentioned about hardware in loop software. Ma'am, if I want to interact that hardware in loop software with the Simulink, then how we can do that, ma'am? Because it is very useful if you are having hardware with us, and if you want to generate some signals out of it, and directly if we can connect with the hardware, then I think it will reduce all the cost and it will make your system more compact. So how can we do that, ma'am?
So the workflow that we mentioned is generating a C code first out of the Simulink model. Just let me go back to that particular slide. Yeah. So the workflow that I mentioned was have the model built in Simscape and Matlab, then import the C code or extract the C code out of the Simscape model and deploy that C code in particularly in hardware. So for example, if just give me a minute, if I were to open let's say this particular page, Mathworks virtual labs, if I type in that. So Mathworks virtual labs talks about various kind of projects or workflows that you can do, and it also talks about low cost hardware or hardware in home such as Arduino and all of this that could be integrated. Matlab code could be extracted and deployed in this kind of environment, as well as there is a environment of Matlab which runs that is a light platform that runs in your mobile. It could be downloaded from Play Store or iOS. The benefit is that different sensor data could also be captured from this kind of Matlab mobile hardware. So IoT experiments also becomes very helpful.
Oh, okay, thank you, ma'am. So, ma'am, it is very useful, and you have showed various links. So, I think I will upgrade my knowledge in the Matlab. Thanks a lot, ma'am.
Thank you.
Ma'am, I have a question. The session was very informative, and it is greatly helpful in understanding few things. I would like to ask that the classifiers that you shown, the library app that it has, does the script files are available to download or not? Just like as previously ANN, like if we use ANN, the script file was available to download. So is it same with the other classifiers?
Yes. Whatever classifier is here, all of the script files are available to download. So I, because here the KNN has performed nicely, I selected KNN. Let's select tree from here, although the performance is not very good, but I can select and generate the function from here. And just like you can see,
okay,
it is an auto-generated code, and the fit C tree function has been encoded.
okay. Thank you very much. Thank you very much.
Any questions? Okay. A warm thank you for thoroughly explained need and challenges of power system design. A session was very useful for having clear concept of analyzing data, developing algorithms, or creating models and programming procedures. Thank you very much, ma'am.
Thank you. Thank you.